All right, let's journey out about 350 light years into the constellation Leo. We're going to talk about a cosmic clock called Pulsar B1133+16. Now, on the surface, it's just one of thousands of these things. But this one's got a reputation for being a little weird. In fact, it was so strange when it was discovered that it was briefly nicknamed LGM4. That's Little Green Men number 4. And you know what? When scientists really started listening in, they found out that nickname was more fitting than they could have possibly imagined. They found a ghost in the machine. So before we get into the really strange stuff, we've got to cover the basics. What exactly is a pulsar? Well, the classic analogy, and honestly it's a really good one, is to think of it like a cosmic lighthouse, spinning out there in the blackness of space, sweeping its beam across the cosmos. So what's actually making that light? A pulsar is what's left over after a massive star dies in a supernova. It's the star's super dense spinning core. We're talking incredibly dense, with a magnetic field that's just off the charts. And from its poles, it shoots out these powerful beams of radiation. As it spins, those beams sweep through space, and every time one flashes past Earth, we hear a pulse. It's like a perfect cosmic metronome. Tick, tock, tick. Seems pretty straightforward, right? You've got a reliable, predictable clock just ticking away in space. But here's the thing. Some lighthouses have ghosts in the machine. And this is where the mystery of Pulsar B1133+16 really begins. Because sometimes the beat just stops. This strange phenomenon has a name. It's called pulse nulling. So what is pulse nulling? It's pretty much exactly what it sounds like. For a few beats, or sometimes for much longer, the radio signal from the pulsar just seems to vanish. It's as if the lighthouse keeper decided to turn the light off for a bit. The signal just goes quiet. Silence. And for our pulsar, B1133+16, this is not some rare event. This isn't a once-in-a-blue-moon glitch. It spends about 15% of its time in this so-called null state. Think about that. That's a huge chunk of its life spent being completely silent. Now, for a long time, the simple assumption was that the whole pulsar just switches off for a bit. You know, like flicking a light switch. But is it really that simple? Is it just one big on-off switch for the whole cosmic lighthouse? Well, this is where things get really, really interesting, because when scientists managed to look at this pulsar across a massive range of radio frequencies, all at the exact same time, they found something that nobody, and I mean nobody, expected. They discovered something they called selective nulling. Okay, this is the absolute key to the entire mystery. On the left, you've got what everyone thought was happening. It's called a broadband null. Basically, when the pulsar goes quiet, it goes quiet everywhere. The lighthouse is totally off. But what they actually found is on the right, a selective null. The pulsar would go silent at lower radio frequencies, just like they expected. But at the exact same moment, it would start blasting out a strange new signal at a very high frequency. It wasn't off at all. It was just changing the channel. So how often does it pull this little switcheroo? Turns out about 6% of the times it appears to go silent, it's actually doing this, going quiet on the low end while broadcasting this mysterious ghost signal way up high at 4850 megahertz. And listen, this ghost signal wasn't just some faint echo. No way. When they dug into the data, they realized it was a completely different animal. It only shows up in this very specific narrow window. Its pulses are much thinner than the normal ones. And get this, they even arrive a little bit earlier than the normal pulse would have. It's almost as if it's being generated by a totally separate engine inside the pulsar. The researchers who found it summed it up perfectly. They said there was, quote, the presence of an additional process of emission which does not turn off when the pulsar nulls at low frequencies. This wasn't just a minor detail. This discovery fundamentally shattered the simple idea of how these cosmic lighthouses are supposed to work. But if you think that's the end of the weirdness, you are mistaken. Because another team of scientists was looking at the exact opposite end of the radio spectrum, and they found another bizarre piece to add to the puzzle. Oh yeah, the plot definitely thickens. This time, scientists were tuning into very low frequencies, way down between 110 and 180 megahertz. And they weren't listening for silence this time. They were listening for noise. And boy, did they find it. Their paper describes finding a much larger intensity modulation at low sky frequencies resulting in narrow and bright emissions. So, what does that mean in plain English? It means that even while the pulsar was in its normal on state, just ticking along, it was also producing these incredibly intense, super short bursts of energy at these low frequencies. And the details here are just wild. The energy in these bright pulses was more than 10 times the average. They were extremely narrow, and they showed up in a very particular spot. All of this points to, yet again, a completely different kind of emission. Some kind of powerful, focused burst that's totally distinct from the pulsar's normal ticking. So let's just put this all together, because it's kind of mind-bending. You've got two completely separate, weird behaviors. At high frequencies, when the pulsar is supposed to be off, you get this weird, persistent ghost signal. And at low frequencies, when the pulsar is supposed to be on, you get these random, super bright flashes. Two different frequencies, two different situations, but both telling us that this machine is way more complex than we ever gave it credit for. So what in the world does it all mean? Well, for starters, it means that our simple little model of a pulsar as a steady on or off lighthouse, that model is in serious trouble. We're literally having to rewrite the playbook on how these things work. And this leaves astronomers with a whole new set of puzzles. I mean, what physical process is even causing this selective nulling? Are the ghost signals up high and the bright pulses down low somehow connected? Could it be that pulsars actually have multiple independent engines that can operate at the same time? And maybe the biggest question of all, is that whole cosmic lighthouse analogy just way too simple? Now, there is a leading hypothesis. The idea is that these strange signals might not be coming from the main part of the pulsar's engine at all. Instead, they might come from a totally different region of its magnetic field called the outer gap. It's like a separate system that just does its own thing, completely ignoring what the main engine is doing. But here's the real bottom line. The big takeaway is that this thing we thought was one of the simplest, most reliable objects in the universe, a cosmic clock, is actually incredibly complex, deeply mysterious, and so much cooler than we ever imagined. And that really just leaves you with one final, awe-inspiring question. If this one, single, well-studied pulsar is hiding this much complexity, just what other incredible secrets are still out there, hiding in the static of the cosmos, just waiting for us to find them?